We're going to talk a little bit about the titration equation. So M1, V1, M2, V2. Nothing special, really. What this says is that if I have a certain molarity and volume of one thing, it will match up with another molarity and volume of, if this is the acid, this will be my base or vice versa. So we use it when we're titrating because the purpose of a titration is to match up the amount of acid and molarity, the amount and concentration of the acid and the amount and concentration of the base as closely as possible, so we see, what it looks like when it's fully neutralized. And we put an indicator in there to show when we should stop and when this neutralization has happened. You know, one of the common ones is strong acid, strong base, and that usually tips out at about 7. You put some phenolphthalein in there. That is actually means that you're a little bit up over that 7 part when that phenolphthalein kicks in, but it's close enough if you're just titrating that way to indicate that you have neutralized all of your acid or your base. And if you're wanting to be more precise about it, you can use a probe when you're doing this. But, say we have 100 milliliters of 0.25 molar HCl, and we want to neutralize that. But all we have is, let's say, 0.33 molar NaOH. So I can calculate how much I'm going to need to neutralize. So if I plug in M1 is 0.25 molar, and then V1 is 100 milliliters, and then I'm just going to plug in 0.33 molar, and then V2, okay? And I don't know why there was 2 M's there. Oh, it's the back of the paper. So M1, V1, M2, V2. I don't know why that was 2 M's there. And so all I do is just divide both sides by the 0.33. Boom, boom. And since it is a higher molarity than the 0.25, I'm going to bet it's going to be less than 100. So 0.25 times 100 is 25. Divided by 0.33, and yeah, it comes out to 75, 75, 75, 75. I don't know, we didn't really care that much about sig figs in this one, so let's say 75.6 milliliters. And so you would need 75.6 milliliters in order to neutralize that. But let's say that we had, instead of HCl, we have H2SO4, and we have 100 milliliters of 0.25 molar H2SO4. Then, if we have that same 0.33 molar NaOH, how much are we going to need? That is the trick right there, because this one is a double protonator. So you could look at it like this. So if I have 100 milliliters and then 1 liter is 1,000 milliliters, and then I get 0.25 moles of H2SO4 in 1 liter, and then 2 moles of H plus for every 1 mole of H2SO4. When I say 2 in the equation when you've got a double protonator, that's where that comes from. So you see, for every 1 mole of your H2SO4, you get 2 moles of hydrogen, okay? Or hydronium. I'm old, I say hydrogen. Deal with it. So I don't need to do all that, though. I can just put it in the titration equation if I'm careful. So I always put the 2 with the volume, or with the molarity rather than the volume, because you're not changing the volume, but the molarity is doubled. Okay, and so it's 2 times 0.25, which indicates the 2 hydrogen you get from the sulfuric acid. And then I've got a volume of 100 milliliters, and then I've got the same 0.33 molar molarity of the NaOH, and I want to know the volume. Same deal, 0.33, but now it's 2 times 0.25 times 150 divided by 0.33, and so 151. 0.5 milliliters of the NaOH. So that's kind of how it works. There's not too much. I don't want to like spend a whole big amount of time on it. Just kind of get your mind around what, when you do this, when you're mixing acids and bases. And, if you see the word titration in a problem, boom, right there. Okay. Adiante, all for you.